Hello everyone. Today I want to talk about this particular topic, big data, new tricks for econometrics. This is purely based on an article which is prescribed by GARP for FRM Part 2 exam under the current issues segment for the 2018 exam. So the article that is prescribed by GARP for this specific purpose is the base for this presentation. So the agenda for this presentation is like this. Initially, I'll be talking about the issues that are unique to big data sets. Today, we are talking about huge volumes of data, a big data. So when I'm having huge amount of data, what are those issues when I have huge amount of data? So we'll initially talk about those issues which are very unique to big data sets. Once I know that, then I'll be moving on to understand how do I manipulate it, what are the tools and techniques to manipulate the big data, to transform the big data, to extract the big data from various sources. And once I have that big data, what are the tools and techniques that are available for their analysis? What are the different kinds of analysis I can do on that huge data? What are the tools and techniques available in front of me? Would I be doing some kind of predictions? And if I do prediction, what is that I need to consider? Then I would be talking about different kinds of approaches to do prediction. One of the most common approach being the classification and the regression trees, where in short we call it as a cart algorithm. And there are a few more techniques that are used widely in the industry. The bootstrapping, which is being used in the financial space quite often, which has been there for quite some time, but of course may not be on big data sets. But again, boosting and bagging are a couple of other techniques which are used in prediction purposes. So we'll talk about what are these, how are they differentiated. Coming to the world of econometrics, where we talk about the quantitative aspects of economics, quantifying economics, economical variables. What is the level of relationship that is existing between the econometrics and the various machine learning methods that I am highlighting here? All these classification and regression tree, boosting, bagging, they all come under the machine learning algorithms. So how do I really link these two fields is one more area that I am going to talk about. So let's get started. What are the various issues? If my data goes huge, if the data that I have to analyze becomes so big, what are the various issues? The first one, the size itself, means I cannot analyze the data using a simple Excel spreadsheet, right? Because Excel at the max has 1 million plus rows. That's it. Or even if I load them into some databases, the speed at which I can access them, the performance of that database may not be good enough. So that mere size means my existing tools will not be sufficient to do proper analysis. I may have to rely on more and more powerful tools for one, handling the data, manipulating the data, and even analyzing the data. So, means there is a complete new set of technology that needs to be studied, understood to really work with big data sets. Whatever the tools, techniques that I currently have for small data sets, they will not be sufficient to deal with the large ones. Then, when I'm saying I have large data sets, I also may be having so many variables, columns. I might be capturing so many variables. Now, if I have to do some kind of estimation or a prediction based on so many columns, there might be a possibility that many of these columns are simply redundant. So, I need to have some kind of a mechanism where the variable selection will occur. So again, there needs to be new kinds of techniques where the selection of the variables happen in a much more sophisticated manner. When I work with small data sets or when I work with non-system kind of scenarios, the kind of models that I can build in the real world majorly are simple linear models. So a simple linear regression is something that I could have built between my dependent variable and the various independent variables or predictor variables. I could have built a simple linear relationship and using ordinary least squares kind of a mechanism or something. But now the kind of relationship that can exist between the variables need not be linear. It might very well be a non-linear relationship, right? Or in some cases without any kind of a distribution assumed. Even when I talk about a simple linear regression, it assumes that the variables are normally distributed. Whereas I don't need to make any kind of a distribution assumption like a non-parametric kind of data, right? So when I'm working with large data sets, I am also interested in looking at more and more flexible relationships between the variables as well. I don't want to confine myself only to a simple linear relationships and so on. So these things tell us that big data sets themselves pose different kinds of unique problems. So understanding big data sets means developing a new skill set altogether in terms of manipulating the data as well as for analyzing the data. Now coming to what are the tools or techniques that are available for manipulating the big data. Let's start how the journey moves. Let's say I have only a million kind of rows, million, couple of million. I can simply handle the whole thing. I can manipulate the data. I can do whatever I want. I can do some kind of analysis on that. A spreadsheet will suffice my requirement. But if the data goes to a few multi-millions, then Excel spreadsheet may not solve the purpose, which means I have to go more towards relational databases, SQL based. Structured query language based databases. Either I can use Microsoft SQL Server or Oracle or probably MySQL, a few more such kind of relational databases. They have they can store much more than a million records. They have probably I can store hundreds of millions also quite comfortably. They have a flexible way to store, manipulate, retrieve. So they have specific queryings. SQL. So as long as my data sets are medium, which has been the case nowadays, or just a couple of years before, until a couple of years before, these kind of databases, which are the structured databases, they are providing various ways to store the data, manipulate the data, and retrieve the data. So SQL, structured query language, has been one of the most popularly used languages to work with the data on the databases. Now, now things are changing. We are talking about not simply gigabytes of data, we are moving on towards the petabytes as well. Terabyte, petabytes. So the data is growing day in and day out. We are talking about several millions or close to billions of observations, which means the standard relational databases that I have been talking about, even they become too huge. Even their capacity becomes very, very limited, which means the SQL, which I have been using to manipulate the data, will become more redundant now. So thus the structure has to move away from the standard relational databases. Now that is where the new generation databases have come into picture, which are typically called NoSQL. It's not SQL. No stands for not only. Not only SQL. They handle much more than that. Right? So that's the meaning of NoSQL here. It's not that we are going away from SQL. It's over and above the typical SQL. Today, if we look at majority of the applications, especially in the e-commerce space or in the banking space, we are talking about real-world applications where the whole data is stored not just in one computer. We are talking about huge clusters of computers. Now, these are not owned by the companies. These clusters are rented. Let's say Amazon maintains such kind of a cloud. Google has its own cloud. Microsoft maintains its own cloud, and few other providers also they maintain their own cloud. Cloud is nothing but a simple large cluster of computers. Now we are creating an application where our data resides on that large cloud, which are offered by these providers like Amazon, Google, Microsoft, which means I'm not buying the storage. I'm not getting into the buying of the processing part. So the manipulation, everything is happening on the cloud. It means I'm actually renting the services rather than buying the storage and all. I'm not buying a few TB of storage or few GBs of storage. So the entire thing is being handled at the cloud. We are renting that. Which means even if a new entrant had to get into this kind of big data, manipulation of the big data, all that party requires is rent, rent on the cloud. So without a need to procure the data or procure the storage space. So even a new startup can work quite comfortably on the big data. Now, let's look at some of the technologies or techniques, tools that are available for manipulation of the big data. So we will, majority of these things came from the Google world, but of course, I see, and for majority of these kind of systems, I see an equivalent version in the open source world as well. So we keep talking a lot about the Hadoop file system. Actually, it has been originated from the typical Google file system. Google had a tool called Google file system, Based on that, an open source file system has come into picture, which is the Hadoop file systems. So this entire file system's objective is supporting large files. Now these large files, they typically get distributed across multiple computers, hundreds and thousands of computers, which means we are talking about the data that is so huge that it spreads across multiple systems. So the Hadoop file system talks about the distributing the data, which is so large, across multiple computers, so that they can be manipulated accordingly, they can be analyzed accordingly, and after that, while presenting, they can be grouped also accordingly. So this entire thing is being supported by the Hadoop file system. Similarly, we are talking about another technique called Cassandra, which is equivalent to the big table of Google. So we are talking about, when I say Cassandra, it's nothing but it's a table. It's a table of data that lies in the Google file system. So when I talk about creating tables in this entire Hadoop file system, so big table is used to create tables of the entire data in the Google file system, whereas Cassandra is a kind of a database that lies in the Hadoop file system. So we talk about again distributing across multiple computers, etc., so that the data access retrieval can happen parallelly. That is the kind of a flexibility that we get with the Cassandra database. Now coming to Hadoop. Hadoop is a kind of a version that came out from the Google's MapReduce as a specific tool. Google had a tool called MapReduce, and Hadoop is a kind of open source version of the same. So this entire framework is to access the data across multiple computers, distributed across multiple computers parallelly. MapReduce also does the same task. So the data that is lying in Cassandra kind of databases, big tables kind of databases, we are trying to access that data, manipulate the data, and show the results. So the Hadoop is intended, this is a kind of an architecture which is intended towards the parallel processing part. So the data is accessed in parallel towards, there will be some kind of identifiers. Using those identifiers, multiple systems are queried parallelly. Hundreds of systems are queried parallelly, data extracted. So the thousands of machines are being queried simultaneously, data is extracted. There will be an identifier for each of the machine. So based on that identifiers, the query goes to a corresponding machine, and whatever are the partial calculations that we are getting from each of the machines, they are all combined. That is what we call as the reduced. They are all combined to create the summary tables. That is how a Hadoop architecture typically works. Hadoop is nothing but we are querying multiple systems in one single go, a distributed system in one single go, by having some kind of identifiers to the machines. Parallelly, the query runs on multiple systems. Whatever are the partial results that are coming from multiple systems, they are aggregated, they are reduced, combined, and showcased back to the user. So that is what is being performed by Hadoop. Then we have another tool called Pig, which is equivalent to the Google version of Sawzall. So it's a language for creating MapReduce jobs. So the Hadoop related jobs, if I have to create, Hadoop related tasks that if I have to create, a language to work with the Hadoop architecture is pick. Similarly, Google had one more tool called Go, but this can be used even with the Hadoop kind of frameworks as well. It's a general computer language, general purpose computer language, especially for doing parallel data processing. Go is a kind of a language which really facilitates programming for parallel data processing. Then we also talk about a few tools like Hive, Drill, Impala, which are having their equivalents in Google named Dremel, BigQuery, etc. So these are all similar to your SQL. They are queries, the tools that actually help you to write queries in a very simplified form of SQL. So basically these are for manipulating with the data, extracting the data from the database, inserting the data to the database. So these are some of the things that are performed by all these tools. Out of them, the one that is very important for me to understand is Dremel, because this Dremel actually has changed the performance related aspect of an SQL query. Even if I have petabytes of data, even if I have huge volume of data in petabytes, I run an SQL query. That entire SQL query can be run in few seconds if I am using Dremel. So now what we could understand here is, if my data goes more and more huge, going beyond the traditional memories of one single system, then having a distributed computer system for storing the data, for manipulating the data, and for getting results much faster is what is the preferred technique. So the big data manipulation requires different architecture, different techniques for storing the data, for retrieving the data, as we have seen Hadoop, Cassandra, Pig, Hive. All these are the various things that come into picture when we are working with big data. Now, once we have manipulated the data, then comes the next part, which is analyzing the big data. So we have extracted the data, we have manipulated the data. Now the next part is, what do I do with it? Right? I should be able to do understand some kind of patterns from the data, some kind of distributions in the data. Now that is what I can do using exploratory data analysis. So this will help me to do a proper data cleaning, because I can identify a few outliers in the data. I can understand the patterns in the data. So based on these things, I can do better data cleaning. And I can do some kind of consistency checks. Of course, there are tools for doing that as well, but in some cases it requires a good understanding of the subject and experience and various other things. I can rely on OpenRefine. So some kind of basic common data cleaning exercises are being performed through OpenRefine and Data Wrangler. But obviously, even after these things are being taken care of, still there is a lot more with respect to data cleaning that needs to be done. Now, once I have some data in front of me, I typically talk about four major tasks. I would be performing one of the four major tasks. Either I would be doing some kind of predictions using the data. So when I'm saying I'm doing predictions with respect to data, majorly it's a machine learning, and that too a supervised machine learning. We have different techniques to do the prediction, right? The description of each and every technique is beyond this article. But just to give you an overview, we have classification and regression trees, simply called as CART. They are used for various prediction purposes. Random forests play an important role in predicting. Then we have various regression methods, which are simple linear regression, or even the non-linear regressions like penalized regressions. We have lasso, we have LARS. Again, I don't want to go into each of these techniques, because here the intention is to understand the big data and how the whole analysis of the big data can be performed. So when I have data, the first task, one of the four major tasks that I can do is prediction, or I can get into a simple summarization. When I say simple summarization, I am trying to get into a data mining exercise where my intention is to identify the patterns in the data. So there are again multiple ways in which I can identify the patterns and the relationships between the variables. And though there are various techniques, regression tools, especially in case of economic applications, even today regression tools are much more popular because they have a good explanatory power. Compared to prediction, for explanatory purpose, regression tools are much more popular. So I can very well use them for summarization purposes. I want to estimate the parameters, or I want to estimate a few, majorly the parameters. So there is an estimation exercise that can be done. I want to estimate the mean of something. I want to estimate the standard deviation of something. So that is what we do in the estimation. And we want to test various hypotheses that are being made with respect to the various parameters or various variables as well. So these are the four major activities that can be performed once the data is in front of us. So when we talk about data science, today one of the newest terms that is being aired in the market, that is a buzzword today in the market, data science. There I do predictions, I do summarizations, I do many more things. So it's a data science is an amalgamation of various tasks that can be performed on the data. So there are so many prediction algorithms I talk about. There is a lot of summarization of the data along with the manipulation. So there are various tools that are available for manipulating the data, for visualizing the data, and various other things that we can do with respect to data. And in many cases, especially when I am doing this prediction models, sometimes my data could be very fat. When I say my data is fat, the independent variables are predictive variables that I am predictor variables that I talk about. See, always the prediction is done by mapping the dependent variable with the set of independent variables. Now, if this independent variables is very large, right, the number of independent variables is higher than the number of observations altogether, the number of data points that I have. So number of it's as good as saying number of columns in the data is greater than the number of rows, right? The number of variables or predictors that I have is much higher than the number of observations that I am going with. In that case, I say my data is very fat. Columns are much higher, so that means they are fat. Whereas in other cases, the rows, which are the observations, are very large with respect to the predictors. There are hardly 2 or 3 independent variables, but I have a few millions of records. In that case, we say that the data is stored. But depending on the kind of data that I am having, my technique to analyze it, my technique to manipulate it, my technique to visualize it should change. So this entire process for analyzing the huge volume of data is entirely different from the process that we follow for analyzing small data sets. Though the underlying techniques don't change, but but overall the way in which they are handled, manipulated, analyzed will keep changing. Now, out of the various four major tasks that I said will perform on the data, one of the major ones is prediction. So here I want to spend some time with respect to prediction. So I want to build a model by taking a data. So model is nothing but, let's say, an equation or a learning. By using some kind of data, I have built a kind of a model or an equation. So this is called as in sample. I've taken a sample, I have built a model. Now I have another data with me. I want to test this model on this data. This is what is called as out of sample. Now, when I run this equation on this data, it should do a good prediction for me. That is what we'll talk about the goodness of my model. So those are called as out of the sample predictions. So my intention is to get good out of the sample prediction. Whenever I say I have built a predictive analytics model, my intention is to say that I have taken a subset of the data to build the model. I'm testing the model on an entirely different data set, and this is the accuracy associated with the model. In many cases, for many kind of relationships, simple models will still do the job. Right? If I'm using a model to do the prediction here, in many cases, simple models will do the job. So if I'm trying to go with various complex, non-linear, non-parametric kind of models, there will be a lot of complexity factor introduced into this model. Now, this complex equation may or may not improvise the fitment out here. So, which means if that is not the case, why do I need to go for a complex model? So, the model, when I am going with the complex model, the intention is it should significantly improvise my out of sample prediction. It need not, if it is just marginally improvising, I may not be interested because there is a cost involved in terms of building a complex model. So that's the reason we talk about penalizing the models. Complex models will get penalized. Now, after penalization also, if the out of the sample prediction is much higher, then the complex model will be preferred. Now, this kind of penalization is otherwise called as regularization. Now, the whole thing generally when we do prediction, we divide the data into various sets. So, let's say I have 1000 data points or records. Generally, I'll split them into 700 and 300, 70%, 30%, or 75, 25. So, this is called as a training data set, which I'll use to build the model. And this 300 will be a testing data set which I'll use for testing the model. So this is what is my in sample, this becomes my out of the sample. Now I'll say that my model is good when the model is developed on this data and is tested on this data with a decent amount of accuracy. And sometimes to see why do I take this 700? Which should go as a 700? What should go as a 300? There could always some kind of arguments, sometimes randomization. All these are possible. Now, instead of this, there is one more sophisticated activity called k-fold cross-validation. Now, what we simply do is the entire estimates and the parameters are typically tuned. Now, what we may do is we will split the data. Let's say I talk about tenfold cross validation. The whole data is split into 10, right? The whole data is split into 10 groups. So the model is built with the 9 groups and is tested with the 10th group. Then similarly, next time the model is built with the remaining 9 groups or another set of 9 groups tested. So when 1 to 9 groups are being used to create the model, 10th group is used for testing. Similarly, 1 to 8 and 10th group are used to create the model, 9th group is used for testing. Similarly, 1 to 7, 9 and 10th groups are used to build the model, 8th group is used for testing. So this kind of an exercise happens 10 times and the parameter that is estimated in each of the 10 scenarios is being averaged out, right? So this is a kind of a 10 k-fold, which is 10-fold cross validation. So I can do this kind of a cross validation to tune the parameter so that the best possible out of the sample estimate comes up. So we have very much improvised mechanisms of doing the prediction, different kinds of techniques, algorithms that are running today in the world, which can help us do much more better predictions altogether. Now, I just want to give some kind of introduction to the various techniques that are being used for the prediction purpose. As I have mentioned earlier, the classification and the regression trees, called as CART in short, is a very powerful algorithm for uh, either classification. When I say classification, my dependent variable is categorical variable. Generally, yes, no, 0, 1 kind of a variable is what I want to predict. Whereas in case of regression, I am more interested in predicting a quantitative or a numerical kind of a variable. So if you look at classification, my objective will be to predict a 0 or a 1, yes or a no, default or a no default kind of a scenario. But this prediction I want to do based on some set of features. My dependent variable will be either the 0 or 1, but my independent variables could be anything. I can use a big set of features as well. When it comes to econometrics, majorly I see the class of models being used are GLMs, generalized linear models. So there is a logit regression, there is a probit regression, etc. In the world of econometrics today, these are the models that are highly used for classification purposes. But when I use the machine learning algorithm today, decision tree is a much powerful algorithm, right? Decision at the end of the process here is a choice, how to classify. So when I say when GDP is greater than 7% and inflation is less than 5%, then the stock price rises, the stock index rises by more than 1% or 2%. So this is how the decision tree typically comes. So various scenarios of the dependent variable, what is the corresponding scenario of the independent variable. So it's a kind of a choice about how to classify the observations. Again, within this decision trees, there are tens of algorithms, out of which one of the most prominent algorithm is the classification and regression tree. So some of these algorithms, they perform really well when we apply to out of the sample prediction. Right, the main advantage of trees over these GLMs is GLMs talk about the linear relationship only between the dependent and the independent variables, whereas the trees can work quite comfortably even when there are non-linear relationships between the variables. Even when there are interactions between the various variables here, it considers all the variables are independent. In case of GLM, it considers all the variables are independent. Whereas in case of the trees, even if there are interactions between the variables, they are also being considered, right? Generally, I mean, the trees have a problem, especially when the relationship is more and more linear. Sometimes they are observed to fail, because in that case anyhow I can very well rely on GLM or any other similar technique, but definitely they work much better when the variables have a non-linear relationship between them. Another important point for you to consider here is majority of these kind of machine learning algorithms that we fit, they are exposed to overfitting problem, or sometimes we say overtraining. They are overtrained, or they have done more than what is required kind of a learning. Means they work very well when applied to the same data, but if the data is changed, their performance falls quite drastically. So it's as good as they have remembered everything in the data. So anything that you ask from the same data, their success rate is much higher. But if you want to test it on an out of the sample, their performance falls quite drastically. So that is what we call as an overfitting problem. Because the tree can go to any level of depth. So the classification goes more and more refined by increasing the depth of the tree. So because of that, there is a overlearning that is happening. So generalizations become very, very difficult. One of the solutions is prune the tree. Don't take the tree so depth, cut it off somewhere here itself. 2 layers, 3 layers kind of a tree. So when the tree is going more and more deeper, the model is actually becoming more complex. So more complex, you need to put a penalty on the complex model. So there is a cost per complexity. So I am more looking at just pruning the tree, but at the same time I can look at a k-fold cross validation, like a 10-fold cross validation, so that whatever the parameters that are coming out, they are refined, they are tuned, so that the out of sample predictions can be much more appropriate. So that is what goes as a part of the classification and regression trees, which are one of the powerful tools for prediction purpose. Then we have a few more such kind of techniques that are being used: boosting, bagging, bootstrapping. So even all these may be used for classification purpose. So the performance of the classifier is improved drastically using these techniques. Bootstrapping. So it's as simple as, let's say I have 1 to n, right? So I'm picking out some observations out of this randomly, probably with replacement, right? So let's say I am having these many records, right? So randomly I am picking a few records, and because if it is with replacement, the same record can come multiple times also. Based on this sample that I am doing on a random basis, I try to estimate the sampling distribution, probably for the mean or the standard deviation or some other statistic. So basically I am trying to take the subset of data from the overall data and try to do the computations on that subset of data. That is what is simple bootstrapping. The only thing is, in bootstrapping, I also, in majority of the instances, I do with a replacement. Now, once I have bootstrapped this data, I can do multiple bootstraps, because in one pick, These are the set of values that are bootstrap. I'll do this process p number of times. So I'll get p different samples, right? Now for each of the sample that I have taken, I create a model. I estimate the parameter for that model. Now I have p such kind of models that can be created. So I am doing an averaging across the models. So basically I am creating a model with one bootstrap. Similarly, with p different bootstraps, I am creating p different models with p different estimators for each of the parameters. Then I am averaging across the models so that the estimator or the parameter is completely tuned so that the out of sample predictions become more and more appropriate. I can use this kind of a method basically for trees where the relationships are majorly non-linear compared to using them on a linear kind of relationships, right? So that's the art of bagging. The intention is to improve the estimation parameter altogether. Similarly, when I talk about boosting, this is a very interesting aspect. Now I'm doing a classification. Initially, let's say I have built a tree, right? Using the training data. Then I have tested on the test data. When I tested it, some data got classified properly, some data got misclassified. Now next time when I repeat this model, all that data that got misclassified, all that observations that got misclassified, they get a much more weightage now. They get more weightage and again the model is repeated. So this model gets refined and refined. The estimates keep refined and refined. The parameters get refined and refined because those observations that are misclassified, they get a much higher weightage. So every time the model is repeated, so I have let's say 100 different models. Now in 100 different models, the classification things could differ. After that there is a OT. So each of the model, for each of the observations, did it classify as 0 or 1? So where maximum number of votes have come, more number of classifications have come, that would be my final estimate. So it's a vote across the various averages on the repeated estimates that I have performed. The only major difference here is the weightages keep changing. So those observations which are misclassified in the previous round, they will get much more weightage. So there is a possibility that they may get classified something differently in the second round. So that's how the voting process, the model is repeated and finally there is a voting process. So the intention here also is I'll see a kind of a predictor performance will improve, right? And this kind of a mechanism can be used literally for almost any kind of model. So even if I am doing a regression, I can use this boosting. Even if I am using logit, probit, trees, nonlinear, linear, any such kind of models, I can very well use boosting on the top of it because here my intention is to improve the predictor performance. So one of those specialized ways of doing the boosting is a random forest, especially when I apply it to the trees. What the random forest does is, let's say I have 100 independent variables or even 10 independent variables. So it will not take all 10 every time. Again, it's a kind of a repeated process. Probably it may take some 3 to 4 variables randomly and try to build the model. So the tree is built with only 3 to 4 variables instead of 10, and this is on a completely random basis. Now, different sets of 3 to 4 will be picked up in different iterations, and a tree is being built. Based on the tree that is being built, the variable's importance factor also comes up. So you are talking about growing thousands of trees. That's the reason we call as a forest, with different combinations of the variables and different combinations of the dependent variable. So because of all these kinds of variations and dimensions, the out of the sample predictions come out to be much more sophisticated, especially again when the relationships are more and more non-linear in nature, right? So all these kinds of mechanisms today, which come from the world of machine learning, can very much improvise the way the econometric analysis is typically performed. Now that's the reason I talk about there is a lot more from the machine learning world that can be used in the world of econometrics. So if you have seen majority of the machine learning models today, they are using the data as IID, identical or independent and identically distributed. But we have so many models that address even the time series kind of a data as well. Even if the data of today is linked with the data of yesterday and the day before yesterday, where the observations are really not independent but have a lot of dependency with the previous observations, which are the time series kind of data. So there are a good number of machine learning algorithms that deal both with IIDs as well as non-IIDs as well. Especially in the areas of causalities, predictions, we can very well use various machine learning algorithms. So there are quite a good number of areas where econometrics can collaborate with the machine learning to phenomenally increase the predictability and come up with much more advanced predictions of out of the sample forecast, right? So this is what I wanted to talk of as a part of this session. These are the various topics that we discussed in quite a good amount of depth in this session. If you have any further queries, I say you can very well get back to me by giving me a call on the number that I have provided below, or you can send in an email as well. Thanks a lot for listening to this session. Thank you very much.